The Macintosh platform is 36 years old, and it's unique for having gone through 3 different microprocessor architecture transitions. Today we'll talk about those transitions and Apple's latest architecture, Apple Silicon. Welcome to Kopec Explains Software, the podcast where we make computing intelligible.
Well, this week, Dave, we're going to talk about the new microprocessor that Apple is installing in all their computers and why it matters.
Yeah, and it's not all their computers. It's the low end of their line that they're starting with, and it's their new M1 microprocessor. And we'll talk about that, but we'll also talk about the history of Apple's different instruction set architectures that they've used in the Macintosh. Mm-hmm.
So I guess we should just first start with why are microprocessors important? Why is this a big deal to make a transition like this?
And we have talked about this before on multiple different episodes of the show, but the microprocessor is the heart, the brain of the computer. It does most of the actual computation. It's the most important component. And there's been many different lines of microprocessors throughout the long history of computers. Microprocessors we talked about on a previous episode, how they came out in the 1970s. Before that, we were working with a smattering of different components that actually got combined into a single component as we started to get more sophisticated integrated circuits. But anyway, different microprocessors run on different instruction set architectures. And you can think about an instruction set architecture as the lowest level language that the microprocessor understands. And we've talked on previous episodes about what programming languages are. Ultimately, whatever a program gets written in, it must at some point get converted into machine code, and that machine code is codified in an instruction set architecture's language. And so there are 2 really popular instruction set architectures that are out there right now. One is called x86-64, and it is the instruction set architecture in microprocessors made by Intel and AMD, and we find it in the majority of the world's servers today and the majority of the world's personal computers. Then the other really big instruction set architecture, although there are many others, is called ARM64. And we find that in the majority of the world's mobile devices today, whether those be our smartphones or our tablets. And then there's all kinds of other instruction set architectures. Maybe you've heard of some of them like MIPS or SPARC or RISC-V. And there's other kinds of x86 architectures like the older 32-bit x86, and there's other ARM architectures that are used in a lot of embedded devices, and there's many more. But the 2 we're going to focus on today when we talk about Apple's big transition is x86-64 and ARM64, but we'll also talk about some of the older ones as well that Apple's used in the Macs going all the way back to 1984.
So let's start there. What was the first microprocessor that Macs were using?
So the first microprocessor that Macs used, thinking about the first Mac 128K that came out in 1984, was the Motorola 68K architecture. And the first chip in that line was called the Motorola 68000. And this was a pretty advanced microprocessor for the time. It came out in 1979. The Mac comes out 5 years later in 1984. It was actually internally a 32-bit architecture, had 32-bit registers and could do 32-bit instructions, whereas most of the personal computers at the time were still using 16-bit architectures like the 8086 or even a lot of computers were still on 8-bit architectures, like the Commodore 64, the Apple II used the 6502. So this was a pretty advanced chip for the time, and Apple used it in the original Mac, and then a lot of the Macs that came after that, like the Mac II, the Mac LC, all the way up to the early 1990s, used newer variations of that chip and that architecture, including the 68020, the 68030, the 68040, etc. But the architecture was kind of running out of steam when we got to the early to mid 1990s.
So what did they do?
So they were seeing a lot of competition from the PC side, of course. Of course, PCs, as we've talked about in previous episodes, were dominating the industry at this time. And they were running Intel microprocessors using the x86 architecture. And so one option for them would have been to transition to the x86. But they really wanted to actually go to something that they would have some kind of control over, and that also they could build in backwards compatibility for their software. And so they actually created an alliance with Motorola, who made the 68K architecture, and IBM. And they called it the AIM Alliance. It stood for Apple, IBM, Motorola. And the three of them together created the PowerPC architecture. And this was based on research that was going on into RISC architectures, and there are two different kind of big families of microprocessor architectures. There's CISC, which stands for Complex Instruction Set Computing, and there's RISC, which stands for Reduced Instruction Set Computing. The idea with RISC, which kind of became popular in the 80s and 90s and continues today, was what if we made the individual instructions really simple, but we could execute them a lot faster? Whereas on the CISC side, which is more like the x86 architecture from Intel, we have more complex instructions that might take longer to execute, but it's kind of more convenient in some ways for the programmer because it does more at once. But the thing is that we really rely on higher level languages written in programming languages that get ultimately compiled down to the instruction set architecture. So it's more important which one we can actually build efficient processors with, because over time, less and less people actually write an assembly code getting down to the metal. And so having a faster architecture is more important than having one that's more convenient to the programmer. So the wave was really towards RISC, and while the 68K had been a CISC architecture and x86 was a CISC architecture, the PowerPC was a RISC architecture. And that was what was going on at the time, is a lot of manufacturers were moving towards RISC architectures. So anyway, so they came out with the PowerPC, and the PowerPC was a lot faster. The early processors were like the PowerPC 601, the 603, the 604. They were a lot faster than the 68K chips that came behind them, and Apple had a strategy for making their computers compatible with the old software.
So why don't you talk a little bit about that strategy, about the compatibility and how important that is when you're making a transition from different microprocessors?
Yeah, the issue is that once you have something compiled down into machine code, we then call the executable a binary. And a binary only works for the architecture that it was compiled for.
So a PowerPC binary, a software that is made for the PowerPC microprocessor, will only work on that for that type of microprocessor, regardless of the upper level language that you're using.
That is correct, unless you do some tricks.
Okay.
And so Apple had to do some tricks. They built in a hardware and software solution to allow the PowerPC to emulate the 68K. And the PowerPC was actually fast enough that quickly PowerPC processors were able to run the old 68K software faster than the software even ran on the 68K chips, even though it was running through emulation. We had a previous episode on what is an emulator, and I'll put a link to that in the show notes. But people might remember from that episode that you always lose performance when you do some kind of emulation. No question about it. You always lose performance because you have to have that extra layer of translation where you're going, here's the old binary, let me convert it into something understandable on the new microprocessor. So there's always some performance cost. But they were able to write something efficient enough that we could actually run that old software performantly on the new PowerPC machines. And not only that, but Apple had another strategy. It was something called fat binaries. And the idea of fat binaries was you'd have a single binary that would have binaries within it for more than one microprocessor architecture. So you'd have both a 68K program and a PowerPC program fused together, and then on the fly, the Mac OS would choose the right one of the two when you double-click the icon. So it just figures out, oh, that's the one I need to execute because I'm on a PowerPC machine, or that's the one I need to execute because I'm on a 68K machine. So developers could go compile their software into a fat binary, and then they could ship one version of their app for both the older machines and the newer machines at once.
That's some pretty complex software, it sounds like.
Yeah, but to the end user, it was totally seamless.
Yeah.
For the developer, it wasn't that bad, but you had to think about, okay, I'm creating two versions really, but they're being fused together. Mm-hmm. And so if you had some low-level code that was specific to the microprocessor architecture, you'd still have to change it, of course, for each of the versions that would get fused together. But as a user, it was totally seamless to you. You just double-clicked. Now, the only downside of fat binaries is that they're bigger because they contain the binary code for both platforms in one. So they have to take up more space. That's why they're called fat. They take up a little bit more space. And by the way, I didn't come up with these names. So if anyone finds them offensive, they're not my names. But anyway, so these fat binaries were a really great solution. And then we also had the emulation technology as well, so that we could still run the old software that was 68K. The only thing that wouldn't work is if you had new software compiled for PowerPC that wasn't in a fat binary form, then that would not run on the older 68K Macs.
So developers had to really think about who's using this, really think about the hardware that they're using their software on. It's really a time where I'm seeing how hardware and software are so intertwined and need to really work well together.
Yeah, absolutely. And the Macintosh was the first personal computer platform, as far as I'm aware, to successfully make a transition like this and really survive it well from one architecture to another. So that was really pretty remarkable. A lot of other computing platforms kind of died out when their original instruction set architecture started to wane in usefulness. So whether they were 8-bit platforms that never made the leap to 16-bit, or there were some other 68K based computers that never made the leap to 32-bit platforms, at least not successfully. They might have had a couple 32-bit machines come out, but the platform died soon after. But Apple pulled off this transition successfully, and it was considered pretty remarkable at the time.
So it wasn't a given that the transition is going to work. It's like a pretty big move for a company to make it.
It's a huge move, and you have to think about the context too. The 68K was a successful line that a lot of other manufacturers were using. They were going out into the unknown with the PowerPC. And they were getting the backing, of course, of Motorola and IBM, which at the time, not anymore, but at the time were really heavyweights in the microprocessor industry. But the whole PC industry was on Intel. And so they were going to, instead of going with everyone else, they were going their own path. And that served them well, it seems, in the 1990s for the most part. Not really. Apple almost died in the mid-1990s, but as far as the microprocessor architecture goes, the PowerPC was competitive with Intel throughout the 1990s. But by the 2000s, things were starting to change.
So Apple needed to make another transition.
They had to make another transition. And what really happened was it was their laptops. So what happened is Intel had really, of course, been successful with the rise of Microsoft and Windows, and they became the dominant player in microprocessors. And then you had this niche player, IBM and Motorola, making microprocessors basically just for some servers, for some game consoles, and for some automobiles, believe it or not, some embedded devices, and for Apple. But if you looked at the volume, like the number of microprocessors shipped, the vast majority were Intel, and then there was a little bit of these PowerPC processors and some other ones too, which are beyond the scope of our discussion today. But anyway, so they were kind of a niche platform, and when you're a niche platform, and when you're not even the whole niche, so Apple's just one part of what these processors are being used for, and Apple wasn't the powerful company we know today in the late 1990s to early 00s, you don't have a lot of market power, and you can't really dictate terms as much. And the issue they were having is that Intel started to really be producing more performant microprocessors than IBM and Motorola. And so the Mac was getting left behind. Even worse, the latest PowerPC processors, which by 2003 were called the G5, people might remember the G3, the G4, and then the G5. The G5 was pretty powerful. It wasn't quite up to where Intel was at the time, but it was really hot and it needed a lot of power. And so they couldn't actually...
You mean hot as in temperature?
Hot as in temperature. It needed a lot of power. It created a lot of heat. And so they couldn't actually shrink it fast enough to get it into their laptops. And this was in the mid-00s. We're talking about 2005 time period. And laptops were just starting to exceed desktops in terms of sales. And so it was really critical that Apple got a performance chip for their laptops. And so they saw that there was just no way forward with the G5, and IBM didn't care about them enough to really put the engineering resources, or maybe didn't even have the ability to put the engineering resources in to catch Intel. And so they had to make a really tough decision, which was, do we switch the Mac over to Intel? When for so many years they had been selling that the PowerPC chips were actually better than Intel chips, and then they have to suddenly reverse face and say, actually, we're going to join everyone else and use Intel. But Intel was starting to make some really power efficient processors for laptops, and there was no future really for the G5 in laptops, it seemed like.
So they had to make a change.
They had to make a change. They didn't really have a choice if they still wanted to stay contenders. And there were also some benefits when they made this transition, which is that Intel processors can run Windows without emulation. And so there were emulators for PowerPC to run Windows programs in the Windows operating system, but they would be really, really slow. Just like we talked about, emulators tend to be slow. And so now by having an x86 platform, the Mac could both run Mac OS and it could also run Windows, which would be a benefit to it as it continued to grow. The Mac was actually in a growth phase in the 2005-2006 timeframe, and they ended up launching the first Intel Macs in 2006. And again, this was another transition, which had a lot of things that go along with it.
So now we have the Intel chip. And is this when Intel was doing their Intel Inside commercials?
Well, they've been doing that for decades, actually. So
really?
Yes, they were doing those, but they were doing them for decades. Yeah. But there were problems. I mean, again, you had the same thing where you had the old software made for PowerPC, and you had to now get it to run on Intel.
And did they make another type of software, like the fat binary, or did they just use fat binary?
No, they made a new fat binary. This time it came from the Next world, and Next was the predecessor company to the modern Mac OS operating system, and we could talk about that for a whole episode. But they had a different name for fat binaries in that world. They called them universal binaries. So that was the new name. And yes, Apple released universal binary technology that allowed developers to compile their apps that they would have both an Intel version and a PowerPC version together in one executable, just like the fat binaries in the 1990s. And they also released an emulator too. A fully software emulator called Rosetta that allowed Intel machines to run PowerPC programs. And it also was relatively performant. So there would even be PowerPC programs that would almost run faster on Intel machines, depending on the program, of course, and the specifics. But it was really remarkable how well it worked, actually, and how seamless the transition was. Because, emulators, like we talked about, tend to be very slow, but actually Rosetta was good enough for the vast majority of software. And with Apple's strategy of universal binaries, the transition was not too bad.
It's so interesting, when a company is going to release something, you think, all right, they just released it. But there's so much prep work to make such a huge transition like this so that your consumers and the people that are developing on this have a seamless transition to a whole new structure.
Absolutely. And it's a change for customers. Customers have to be worried about their investment. Like, for example, when a customer has a machine on the old architecture, eventually software developers are going to stop making software for it. And there's another issue, which is actually Apple will eventually stop releasing new versions of Mac OS for it. And that happened pretty quickly. It wasn't too long before Apple stopped releasing versions of Mac OS, what was called Mac OS 10 at the time, for PowerPC processors. Actually, only 2 releases still existed for PowerPC. Mac OS 10 10.4 and Mac OS 10 10.5 came out for PowerPC after the Intel transition started. So they basically dropped support for their older computers after about 2 or 3 years after this transition happened. And so when we talk about the new transition, they got to be worried about that now. This also happened back in the 90s, but Apple had a longer period where they were still supporting the 68K machines because they had a pretty big install base versus the new PowerPC machines, and Apple had to really keep every customer happy because they were really in dire straits back then. But anyway, there's always this issue of if you have one of the machines with the old architecture, you're going to stop getting support more quickly than normal when there's a switch to a new architecture. And so a lot of people are probably thinking about that right now.
So we're in a new or another, I guess, transition point for Apple. They've just released their new computers or their new laptops with their new chip.
Right, and they had telegraphed this. They told developers in the world already that they were going to be making this transition many months ago. They said, okay, we're going to be moving from Intel to our own silicon. And Apple designs its own microprocessors for its iPhones, for its iPads, for its Apple TV, for the Apple Watch, even for things like AirPods. They design microprocessors themselves for all of those. And so they have a lot of experience, actually. They've been designing their own microprocessors now for more than a decade. And they actually bought some microprocessor companies back then, still even under Steve Jobs. One called PA Semi was one of the major ones. And so they actually have a lot of experience building or designing at least microprocessors that end up getting manufactured actually by other what we call fabs, like TSMC, Taiwan Semiconductor, is the main one that actually manufactures Apple's microprocessors. But in terms of design, Apple has a lot of experience and they've been remarkably successful. The performance of Apple microprocessors in their smartphones, for example, are 1 to 2 years ahead of the best manufacturers of microprocessors for the Android side. So we're talking about ARM is the architecture used in most smartphones, including Apple's own silicon. And if you look at the different ARM manufacturers, you look at companies like NVIDIA or Qualcomm or Broadcom, they all make ARM microprocessors. Samsung does as well. Their microprocessor is not even close to as performant as Apple's. And you don't have to take my word for it. You can go look at different benchmarks and see that. So they've been having this great success in their processors for their smartphones. And it's kind of like, well, why are we still sticking to Intel with our Macs when we could actually maybe be doing an even better job ourselves on the Mac side? And so they decided to make another transition. But for customers, I mean, there's a pro and a con again, where yes, we're going to get more performant, more energy efficient microprocessors in these new Macs, but we're going to be leaving behind a whole set of software. And even more than that, the big thing we're leaving behind this time that we weren't leaving behind in the previous transitions is the ability to run Windows. Now, it's possible in the future there'll be a remedy for that because there is a version of Windows for ARM, in fact, and it's possible that that Windows for ARM might be able to be installed on future Macs or at least run in some kind of virtual machine. So there's really a possibility there. But in terms of compatibility with most Windows programs today and the ability to run the mainstream version of Windows today, we're going to be losing that. And so that's going to be a big impact for a lot of people who rely on their Macs to use both Mac programs and Windows programs on the same machine.
Yeah, that is a big shift, something that I hadn't thought of yet.
Yeah, it's a big deal for a lot of people. But in terms of the software strategy for Mac OS, Apple is following the same playbook again. So they're having both universal binaries, so the ability for developers to ship versions of their apps that contain binary code for both Intel and for Apple Silicon in the same package. And then they're also shipping a new emulator, and they're calling it Rosetta 2. The one from PowerPC to Intel was called Rosetta, so the new one's called Rosetta 2. And apparently, early benchmarks seem to show that Rosetta 2 is very performant, and that we're actually seeing programs running, in some cases, as fast as they ran on the previous generation of Macs on these new Macs. But this transition, Apple says, is going to take up to 2 years. And so just last week, we had the first release of some Macintoshes running on this new architecture. And the first chip in this new architecture designed by Apple is called the M1. And so we're seeing the MacBook Air, the 13-inch MacBook Pro, and the Mac Mini be the first machines to get an M1 chip. But the M1 is a pretty low-end chip compared to what they plan to come out with in the future, which is why they didn't have the more professional line Macs like the Mac Pro or the 16-inch MacBook Pro have a version of the chip yet. So we presume that there's going to be more powerful, more exciting, more performant versions of the chip that are going to come out over the next year to 2 years that are going to make its way into some of the higher end Macs. But even this first version, this M1, is already much more performant than the chips that were in the equivalent Macs right before. So if you bought a Mac in the last few weeks, my recommendation to you is that you return it and you go buy one of these new Macs running these M1 chips. Not only will it future-proof you against getting your machine obsoleted over the next couple of years, but it will also give you a much more performant machine. So unless you need to run Windows or you have some very specific software needs, then it probably makes sense to either return that Mac you bought in the last few weeks, or if you've been waiting for a long time to buy a new Mac, now is a good time because these new chips are just getting released. And so you're going to be on this new wave for the new platform.
That's pretty exciting.
Yeah, no, it is pretty exciting. But it's also controversial in some ways because there are people who really rely on stability and the ability to use software that's been around for a long time. Let's think about the different eras though. And if you think about it, actually we had a reasonably long time with the Intel era. So we had the original 68K architecture from 84 to 1994, which was 10 years. Then we had the PowerPC from 1994 to 2006. That's 12 years. Then we had Intel from 2006 to 2020. That's 14 years. So if you think about it, we actually had Intel on the Mac for the longest period and the longest actually era of stability of any of the architectures. And so maybe, it's time. It seems like, you ever hear that song, I'm like a bird, I only fly away, right? The Mac is always in some kind of transition, it feels like. And there's been a lot of other software transitions that we could talk about on another episode. But in terms of instruction set architecture, the Mac has never stood still and just stayed with whatever they've been using just for the sake of compatibility. Apple's always been willing to transition it to a more performant chip architecture as the need arose. And it seems like they feel like they're getting some kind of competitive advantage by making this transition. Early benchmarks seem to say yes. And again, these machines are just coming out right now, so we haven't got really thorough benchmarks yet. But it looks like for the class of power supply, so how much power the chip is actually using versus similar chips, we're getting really great performance out of this first set of Apple Silicon.
It's pretty cool.
Yeah. All right. Well, thanks so much for listening to us this week. Rebecca, tell people how they can get in touch with us on Twitter.
Our handle's at Kopec Explains, KOPEC EXPLAINS.
And I also want to remind everybody to leave us a review on your podcast player of choice, whether that be a 5-star review on Apple Podcasts, we would love that, or just following us on Spotify or starring our episode on Overcast. Wherever you're listening, if you leave us a review or a like, it really does help other people find out about the show. So thanks for listening, and we'll see you next week.
Thanks for listening.